Yeah, welcome. In this session, we are going to be um, we're going to be taking a dive into gradient boosting, gradient boosting. All right, excuse me, gradient boosting. Let me get a red color and make this bigger. Right, excuse me. We're going to be looking at gradient boosting. Trying to get the correct marker. Right. So now, what's gradient boosting? Uh, and there are a few variants of it. There is, XGBoost. You have XGBoost. You have Cat Boost. You have other boosts and all of this boost. Then I think Light GBM. I'm correct. Right. So, but yeah, generally, what is gradient boosting? So, gradient boosting is a supervised learning ML technique that improves all of the things that we've seen inside decision trees, random forest and all of that. One of the problems with random forest is actually an improvement of decision trees, but one of the problem with random forest particularly is that the trees are independent, right? They don't touch each other. You have three trees. Let's say there is one tree here. Sorry, like this. It goes like this. This is tree one. Let's call it T1. There's another T2, and it is something like this, right? Then there's like a few till Tn, however many trees that we have, and that one is like this, and like this, and like this. Let's see something like that. So now here's the thing: each of these trees, let's say this is a classification problem, right? We're going to take a vote, right? When we get to this prediction part, we're going to take a vote. The interesting, the one of the weakness of random forest this like a whole random forest. One of the problem with random forest is that these trees, if this particular tree is terrible, like if it is a poor predictor, we don't care, right? Random forest does not care. It is going to give you the same exact weight, the same exact preference as the ones that actually are good predictors. So if you have five bad predictors, for example, and you have three good predictors, all of those five bad predictors, if they in a way, let's say that happens and they all predict one class as being correct, and all of the good predictors are like actual good predictors predict another class, well, the other ones are going to take the lead. That's like the beauty and the burden of democracy, right? So, and that is one of the things that gradient boosting attempts to actually fix. So instead of like training multiple independent estimators and bringing them together, then aggregating them, we can actually take it a step further and learn by mistakes. That is, instead of having all of these things in isolation, we take this first particular tree, we learn from it, we use it to make prediction, then also train another one, which is going to be this one, make better prediction, then pass that into this one, and again make better prediction, like that till we reach convergence, or we stop, we choose a finite n estimator. So instead of independently having multiple estimators that trains without communicating with each other, we actually train them, you know concurrently, like one after the other, or is concurrently right, or like, okay, sequentially, like we train one, we obtain some facts, we use the facts in the one that we've trained, we use it to train the next one and update our learning till we actually converge to what is true. And that is basically how gradient boosting works. But let's actually look at the way it happens, the way it is done. So now, I'm going to start really by listing out the step. I think that's going to be the right thing to do. Listing out the steps that it entails, then showing. But that's going to make this video very long. So instead of doing that, let me just walk you through it with a simple data set. So let's say we have a data set, and it's going to be a single data set of x and y, so that this is going to be really easy for us to knock out of the park. So 1, 2, 3 for just a very simple data set. Then we have maybe 1, 4, 2, 3. So we want to use all of the x's to predict all of the y's, right? Now, the first thing that we are going to do is we are going to firstly obtain um, prediction for the first model. So you can think of, I told you earlier also, gradient boosting also uses multiple models, trains multiple, we call them base learners or weak learners, multiple weak learners. So the goal is to combine all of these weak learners to form just one strong learner. And uh, that comes from a kind of, that results in a kind of formula where the last thing is always, um, you can say f of, let's say, mx, that is going to be equals to, which is like the last thing is going to be equals to f naught of x, which is going to be the base one, plus, then we can go summation of learning rate, if I'm correct, h of x, like this. Then we can, or let's say hm of x, then m is going to start from 1 till capital M, which is the last thing. So what we are saying basically is, for us to have a final model, like a final output, the uh, answer to that, that is the final model that performs well, is going to be, let me rewrite it here, like just break it out. Let's say our m equals to 5. Oh, no, no, 5 is going to be too long. Let's say m equals to 3. That's going to be f of 3 of x, of cap, like the whole thing that we're going to need, to train, is going to be f naught of x, that is the very dumb constant model, like it predicts, let's say something like averages, a single value, plus the first model, that is going to be uh alpha multiplied by h1 of x, plus alpha, which is learning rate. You're going to understand what learning rate means shortly. H2 of x, plus learning rate h3 of x, right? And each one of these, h1 of x, weak learner 1, this is the first weak learner. So we can see weak learner 1. This is our weak learner 2, learner 2. Then this one is weak learner 3. Now, and this is just basically how gradient boosting work. And this one is learning rate, learning rate, learning rate. So I'm going to show you what learning rate means shortly. So this place here is actually where we are going, and you're going to be seeing this step one after the other. So what's the first step? The first step in gradient boosting, for example, for this data set, is going to be 1. Let's come at the top here and say step 1, and that is going to be to get f naught of x, which is going to be predict some constants. So that is going to be a model that predicts some constants. And good practice, especially when you are working with regression, where your loss is going to be squared error, for example, the best thing to use is the mean. The average is the best thing to predict. So basically, we are saying in step 1, get some uh, output, some model that actually predicts a new y, and that model is going to only predict one thing. And what it's going to predict is the mean, right? We are going to predict the mean. So we are going to say f naught of x is going to just be 1 plus 4, 5, 10. So that's going to be 10 over 4. And I think that's going to be 2.5. Right. So it means that for f naught of x, we can come here and say for f naught of x, We are going to predict this is going to be 2.5, this is going to be 2.5, 2.5, and another 2.5, right? And our step one is done. Now, step two is going to be to compute the residual. Compute the residual, the residual. And what's residual? You already know what that means by now. Residual is the difference between your real value and the prediction. So in that case, residual is going to be y minus f naught of x, right? Y minus f naught of x. And um I don't really like want to make this very complicated, but if you really go like study materials or the gradient boosting paper itself, you're going to see that this particular y minus f naught of x there is really the negative gradient of this particular f naught, or the negative gradient of the loss with respect to this particular f naught. And if you write that down, it is something that will look like this. That is this particular um, residual, and that's going to be, if I get it correctly, it's going to be the negative derivative of derivative of the loss. Loss is going to be yi, minus y cap, something like that. But in this case, our y cap is y f of f naught, y f naught, right? So all over the f naught like this. So the negative derivative of this loss, excuse me, with respect to that particular f naught for squared error is going to be this particular mean here, this particular value here. Where is it? I think I might be missing it. Yeah, it's going to be this. It's going to be y minus f naught of x. So that is just the reason why we are not going so deep into this, and you can just take step two as this particular thing here, right? Y minus f naught of x. And if you think about it, really what you are doing is you are computing the negative gradient of the loss function, this loss function, with respect to the current prediction that we have, which is the constant, this constant prediction. Yeah. And basically, what that tells us, and this is something that you're going to understand a lot more when we get to deep learning. What this tells us is how do we adjust the prediction, the current prediction that we have, to reduce the error, right? The current prediction from the weak learner, how do we adjust it to reduce the error that we're going to have? So now, if we say y minus f naught of x, that's going to give us r1. So if you come here and say r, or you could call it r naught if you want, or r1, whatever, that is going to be 1 minus 2.5, 4 minus 2.5, 3 minus 2.5, 3 2 minus 2.5, then 3 minus 2.5, like that. So let's say you have some value. I think this is going to be negative 1.5. This is going to be positive 1.5. This is going to be negative 0.5, if I'm right, and this is going to be positive 0.5. Now we've gotten our R naught. Now, what's the next thing to do? The next thing to do, which is going to be our next step, is going to be, let's call it 3 here, step 3, and it is going to be to fit a model that is another weak learner on the residual. And what does that mean? We are going to be using this x, we are going to be using our features, our x's. We are going to use it not to predict the y or the f naught of x, but to predict the residuals. Is that right? Like we are going to be using that to predict what? The residuals. So, and the model that we are going to be fitting right now could be a tree-based model, could be a decision tree, or could be a linear model. So at the end of the day, What are we going to have? We are going to have, let's call it h1 of x. So we are going to have h1 of x, and that's going to be equals to some, let's say some weight. Let's call it some weight x multiplied by, okay, let's actually use the standard thing that we are familiar with. So we can say some wx plus b, right? So let's say this is like a linear model, right? So we are going to get some weight and some bias. Is that right? So let's say we've solved this. And what does that mean? What I'm trying to say is we are going to train something like a linear regression using X, and we're going to use that to try and predict um R naught. So if you are doing it in something like X scaling, I'm just saying it is going to be something like model dot fit. Then we open our bracket and say X comma R naught, right? So we are using our x's, this x here, we are using it to predict R naught, not Y. And this bit is extremely important. We are using it to predict R naught and not Y. So once that comes out, let's say it comes out, then we are going to have a value for our weight, which is going to be some value, and bias is going to be some value also. So once we have those two values, we are now going to get our f1 of x. What does that mean? We are going to have some values for h1 of x. Where are you? We are going to have some values for h1 of x, that is for this prediction here, this prediction here, this prediction here, and this prediction here, right? Which is going to be h1 of x. Now, our new f1 of x should just naturally be what we've learned from the previous one. So it should be something like f naught of x, which is the previous model here, plus what? h1 of x, right? That is what we've learned uh from fitting x to the residual, right? But now, if we do this, let's say this value for h1 of x, if it is too large in the positive side, we are going to take too much of a jump. Don't forget, computing residual is taking the negative, is computing negative derivative of the negative gradient of the loss function with respect to the current prediction that we have. So if we take too much of a big step, we might miss convergence. That is, we might just miss the right prediction. And if we take too little also, it might just be too much. So that's what brings us to the idea of something called learning rate. So instead of doing this, which is going to be wrong, instead of doing this, which is going to be wrong, this one here, we actually say f1 of x is going to be equals to f naught of x plus learning rate alpha, which is going to be some value that is less than 1, multiplied by h1 of x. So let's say our h1 of x predicts 2, value 2. Instead of saying um, yeah, 2.5 plus 2, which is going to give us 4. If we choose learning rate, if we say alpha equals 0.1, so 0.1 times 2, if we come here, the new notebook, if we come here and do, excuse me, yeah, we do 0.1 multiplied by 2, it is very funny that I don't know what 0.1 multiplied by 2 is. That's 0.2. So if we come here, we are going to get 0.2. Then instead of saying f naught of instead of saying f1 of x, which is what this one would have given us, instead of saying f1 of x equals to 2.5 plus 2, which is 4.5, we are now going to have 2.5 plus 0.2, which is going to now give us 2.7. So this one would have given us this one here. Let me see what I'm doing. Okay, right here. So this one would have given us, this one at the top here would have given us 4.5, and this one here, the second one, gave us 2.7. Now don't forget, the real place that we're actually going to is somewhere around what, 1. And you're going to see that 2.7 is still close. 4.5 is like drifting all away. And please don't forget that we are using fictitious values, right? So, uh, yeah, that is the whole idea of, um, and even this one here, this one here, you still have to use the prediction. Each one of X is going to be some prediction that we get from using this weight and bias here, from what we fitted. So that is basically what gradient boosting do. So what's the next step? The next step is we are done with fitting the first one. What's the next step? We fit we redo this whole thing. And how do we redo it? We go for, after getting f1 of x. Yeah, let me show it to you. You would have come here and you've gotten f1 of x. The next thing is to compute r1, the residual. So all of the values that we got from computing f1 of x, we do one, y minus that, y minus that, y minus that, y minus that, we get r1. Next step, we come to this place, we've computed residual, we come to this place, we fit another model to predict, we do residual, on and on and on like that, till one, we either reach convergence, or we stop it at a particular n estimator, that is number of stuff. And that brings us to this final equation. This is like the true equation that exists, because we do f naught of x, learning rate plus h1 of x, which is what you have here, learning rate plus h1 of x, this one here. Then again, we had h2 of x, learning rate plus h2 of x, like that. So repetition till you get to convergence, or you choose any number of estimator that you want. Now, what does that tell us? That tells us that this is just an improvement on the models that we've seen before, and it has just two extra parameters, extra hyperparameters, which are number one, n estimators, right, and learning rate. Learning rate also. Then another one is the type of learner that you want. So it could either be a tree based learner, or it could be a linear based learner. So yeah, that is how gradient boosting works. That's just the intuition behind it. That is the way the flow happens. So let's quickly code an example of it. So let's say import pandas as PD, import, say, from Xgboost, import SGB. Let's just look at a regression problem also. Or you could look at classification problem if you want. Maybe we should look at the classification problem. SGB classifier. So from sklearn dot dataset. That's not correct. From sklearn dot dataset. Let's import that load underscore breast cancer dataset. Then for that thing, from sklearn dot model selection, import train test plate. Then from sklearn dot metrics, I'm going to import classification report. You can run that, and we can just load our data set and say x equals load underscore breast cancer. Then I can do data, and here I can say load underscore breast cancer, and I can say target. So just to show you what the data looks like, let me see, as frame equals true, yeah. But if you've been following this series for a while now, you should know what this data looks like. So we are going to have all of this. It's still coming up, like all of this to predict whether somebody's going to have cancer, breast cancer or not. So, and it's a binary classification problem. So what we just do is we say X train, Y train, X test, Y test equals train test split X comma Y test size equals 0.2 random state equals 23 stratify equals Y. All right. So we run that. And the next thing we want to do is fit the model. So I can say model. No, this is wrong. Is this X train X test, Y train Y test, X train X test, Y train Y test. So I can say model equals um SGB classifier, and inside SGB classifier, you can have different hyperparameters, but for now, the only thing that we are passing is random state. Then I'm going to say model dot fit X train, comma Y train. I'm going to do train pret equals model dot predict X train test pret equals model dot predict X test. And we have an error somewhere. It says invalid classes inferred from unique values of Y. Our splitting is wrong. So we say X train X test, Y train Y test. Let's check our X train and see. X train is this perfect. Let's check Y. It's actually complaining about Y. Aha. So this is the problem. Our Y is not supposed to be. So let's rerun this and rerun this. Aha. So it should work now. So our Y should be a single column of binary values. So if we run this now, perfect, it works. So we can just print f string train result or train report. Now we can go classific. I'm not sure we imported classification reports, did we? I'm not sure. We did. I think we did. So classification report of Y train, excuse me, Y train, comma train pret, and then let's just copy this old one here and paste it here, and we can go Ctrl D test pret, then run that. So we see that this is the output. The model really performed incredibly on uh, the test set, even though it is overfitting the training set. So, but like I said, you can always play around with hyperparameters and do an estimators equals maybe 3, and that should like majorly impact the output. Can you see? So it has majorly impacted the output, but you still have to find that balance from just playing around with things. But like I said, we're going to be having a full there's a full upcoming video on how to do hyperparameter like a pro, and when we get to that, you're going to see how to actually get that. So that is that gradient boosting, and we've seen an example implementation with Xgboost. So thank you for tuning in. See you guys in the next one. Bye.